Hello everyone, let's solve the problem search insert position. Given a sorted array of distinct integers and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. Okay, you must write an algorithm with O of log and runtime complexity. Alright, fine. Let's first try to understand what the question is saying. Let's take this example 1356. We have 1, 3, 5 and 6 and the target given is 5. We are supposed to return the index of the target if it is found. So what is the target here? It's 5. Is it present? Yes. What is the index? It's 2. So 2 is our answer. Now let's check another example 1356. Okay, same, but the target is 2 this time. So is 2 present here? No. So if we insert 2 in this sequence, in this sorted sequence, where would it go? Where will we place this? We will place this here, right? This is 0, index 0, 1, 2, 3. We will place 2 here. And as soon as we place 2 here, what would be the new index of our 2? It would be 1. And all these would shift forward by 1 index, isn't it? So we are supposed to return this. So since it is a question of searching, we are being said to do it in a O of log n time complexity, right? So why not just try it in a naive way? What can we do? We can do linear search, right? So let's say we are at index 0. What can we do? We will keep moving forward in the array until our I is not in bounds, or you can say till our I is in bounds, and until we have a number which is less than target. What do I mean by that? Let's say 1, 2, 3, 4, 6, 7. The target is 5. Okay, 0, 1, 2, 3, 4 and 5. We will start from here and move forward. Till when? Till we encounter a number which is greater than our target, right? If this is our number and we encounter a number which is greater than target, that means this 5 cannot go beyond that number, isn't it? We will have to stop right here, right? And then we will be able to accommodate 5 in this place, isn't it? So we will keep moving until we have a number, we have a index or a element which is greater than our target. All the numbers are distinct, that is given, right? So that's what we are doing until we have a number which is not greater than our target. We will keep moving forward. That is, while our current number is smaller than target, we'll keep moving forward. As soon as it becomes greater than target, we will stop, or say if we move out of bounds, we will automatically stop, and then we will return that index. Let's try. Okay, this would run, would work. Still see. Okay, this is just the naive approach. We are not supposed to do like this, right? We will still have a look what it actually is doing. 1, 2, 3, 4, 5. Say our inserting element is 6. We are here. Is it less than target? Is this number less than target? Yes, it is less. Move forward. Is it less? Yes, still less. Is it less? Yes. Is it less? Yes. Is it less? Yes. Is it okay? No more. Is it less? We have moved out. What is our index now? 0, 1, 2, 3, 4 and 5. So if we insert 5, we will have to insert it. I mean, if we insert 6, we will have to insert it in index 5. That is after the array, right? So this is our answer. Now let's say we have something like this. We have target 4. We are here. Is it less? Yes. Is it less? Yes. Is it less? Yes. Is it less? No. We stop. We return I. Why return I? 0, 1, 2 and 3. If we insert 4, it will lie here, right? That would be index 3 and this will become index 4, isn't it? So that's what we are doing. So this, it has a time complexity of O of n and constant space complexity. Now we will look for a better approach, because we have been given this, we have to do it, right? We have to do it in a complexity of O of log n, right? What can we do? First of all, we are given this time complexity. Also we are given that our array is sorted. So what can we think of directly? What can we infer from it? Our array is sorted, right? We are supposed to search. Our time complexity is log of n. What does that mean? This means we are supposed to do binary search. Very simple. Direct inference, right? Binary search. Okay. Now, how do we do a binary search? Say we are given this array. Let's take this simple array 1, 2, 3, 4, 5, 5 and 6. We are supposed to say find 5. Let's now just talk about searching. Let's forget about insert position. Let's forget about it. Okay, we are given this array. We are supposed to see if 5 exists or not. What do we do in binary search? We take 2 pointers, one at the beginning, that is low, and one at the high. Let's call them L and H. Okay, now after that, what do? We take out the find the middle position. Now what is the middle? The indices are 1, 2, 0, 1, 2, 3, 4, 5. Now what is the middle of this? It is 2, right? This is the middle. Okay, now we have 5. Is the number which is present in the middle, is it greater than 5 or less than 5 or equal to 5? We can clearly see that it's less than 5, right? 3 is less than 5, isn't it? What does that mean? It means that if the middle position is lesser than the target, that means our target lies to the right of our middle, isn't it? We can clearly see our target middle is 3, our target is 5. That means 5, because the array is sorted, 5 will lie after 3, right? Not before 3. The numbers before 3 are smaller, right? So there is no point in searching for our target to the left of 3, right? We will initially, this was our search space. We will now make our this one our search space, right? How do we do that? We will shift this low to here, the next to mid plus 1. Why not mid? Why mid plus 1? Because it's greater than 3, right? Greater than the middle. So why just include it the second time? Let's just forget it. Okay, now what is the middle position of these two indexes, 5 and 3? What is that? 8. 8 by 2 is 4. This is our middle. Okay, now we will see if the middle position is less than target or greater than target or equal to target. We see that our target is equal to the element on which we are standing right now. That means the target is present. So what do we do in that case? We return the mid or the middle. What is middle? It's the index. We return 4. Fine. That's how we do a binary search. Say instead of 5 we had 4. Our middle would be this. Okay, now we will see, is the current element greater than our target? Yes, it's greater, not less nor equal. So what do we understand from this? That means our target lies to the left of middle, isn't it? In that case, what we will do, we will shift this high to the position just one before mid. Okay, because there is no more point in checking this side if our target lies or not, right? Because it's smaller, it will definitely lie to the left hand side. Okay, now we are here. Let's take out the middle now. New middle. What is the new middle? It's the same. Okay, let us see. Is the current element less than middle? No. Is greater than middle? No. Is it equal? Yes. That means we have found our target and it lies on in the index middle. Okay, so we return middle. So that's how we search. Now the thing we are left with is, what is the insert position if that number doesn't lie? Okay, so the first part of our question says find the target. Okay, let's say our target is 5. What we will do, we'll take a low pointer, we'll take a high pointer. Okay, let's implement that. 0, high will be nums dot length -1. Okay, while our low and high have not overlapped, we will find the mid. Why not just low plus high by 2? In order to avoid integer overflow, we do this one. Okay, always do this one. Fine. Okay, if our middle element is equals to the target, that means we have found it, return that index that is mid right away. Otherwise, if target is greater than our middle element, do something. If it is lesser, if the target is lesser than middle element, do something. Now what will we do? Let's see. We have 5. Our middle is initially this, right? Is target less than this or greater than this? Clear, we can clearly see it's greater, right? That means target will lie this side. And now we will reduce our search space. We will move low pointer to the next index of mid, this one, which means low becomes mid plus 1. Otherwise, let's say we have a 2. Okay, this is our mid. Is target greater than mid? No. Is it less than mid? Yes. That means our search space will be this. We'll move high pointer to the just previous index of our mid, that is mid minus 1, this one, right? Let's do that. High equals to mid minus 1. Okay, so till here we will address the case when the target is present in nums. What about the case when we don't have the target present in the array? Let's see. Let's say we have 1 2 3 4 6 and 7, index 0 1 2 3 4 and 5. Let's do a binary search. We have low, we have high. What is the middle? This is the middle. Our target is this one, right? Okay, we can see target is greater than middle. We move here, our search space reduces, we move to the right. Okay, new middle, this is the new middle. Is it greater or smaller? Target is smaller than the middle element. That means target lie to the left of mid. Fine. Move the high pointer to left of mid. Fine. What is the new mid? This is the new mid. What is the mid element? 4. Is target greater than 4? No. Yes, it's greater than 4, right? That means our search space moves to right side. Okay. Move left to the next of mid. Now, what was our condition? We are supposed to keep a check until they don't collide and exceed each other, right? Low less than equals to high. That means they can either be equal or low can be less than high. Low can't go beyond high or high can't move before low. But in this case, low has moved beyond high. That means our iteration will stop. Okay. Now let's see one thing. If we insert 5, if we try to accommodate 5, it will fall in this position, right? So what will be the index of this place? It will be 4. And this 4 will become 5. They will move by one place, right, to the right. So our insert position would be 4. Now where is our low lying? Our low is lying at 4. So this low is our answer. Okay, let's see another example. See, we have 1 2 3 5 6. Okay, 1 2 3 4 5. Let's take one more. Okay, let's say our insert element is 4. Low, high, mid. Fine. What is the middle? It's 3. Target is greater, that means search space is the right one. Low. What is the new middle? This is the new middle. Is the middle element greater? Yes, it's greater. Target is less than middle element, that means this is our search space now, right? Move high to the left of mid. Fine. Okay, what is the new mid? This is the new mid. Is the middle element greater than 4? Yes, it's greater, right? In that case, it's greater, right? Or we can say target is less than our middle element, that means 4 will lie to the left of mid. In that case, what we will do? We will move high to left, mid minus 1. Now our condition has been broken. Now let's try to observe something. We'll stop right here. Okay, now let's try to observe something. These are the indexes 3 4 and 5. If we try to accommodate 4 here, where will it go? it will go to here, right? It will go to here. What will be the index of this place? 0, 1, 2 and 3, right? And all these would increase by 1, increase by 1, increase by 1. They will move one place to the right, isn't it? So our answer is this index. Where is our low lying? Low is lying at 3. So in this case, low is again our answer. So if the element is found, if target is found, return mid. If not found, return low. Fine. Return low. Now let's try to run it. Works fine. Let's submit. There we go. So this is how we solve this problem. Simple exact binary search with just a little modification. Modification from by how? By doing some observation, right? The time complexity is O of log of n. That is what the question has demanded. And space complexity is constant, obviously. So this is how we solve this problem. If you like this video, do hit the thumbs up button, share this to your friends, and definitely subscribe. And I will see you in the next video. Bye bye.